Hello, everyone. Alright, I actually found this really great Twitter thread from Professor of the School of Chemistry of the University of New South Wales, Professor Polly Thordarson, I believe his name is pronounced, explains really great why viruses are dissolved by soap. So I thought I'd read it here for people that don't want to read it themselves, but still might be interested in how this works. So, why does soap work so well on the SARS-CoV-2, the coronavirus, and indeed most viruses? Because it's a self-assembled nanoparticle in which the weakest link is the lipid fatty bilayer, a two-part thread about soap, viruses, and supramolecular chemistry. The soap dissolves the fat membrane, and the virus falls apart like a house of cards and dies, or rather, should we say, it becomes inactive, as viruses aren't really alive. Viruses can be active outside the body for hours, even days. Disinfectants, or liquids, wipes, gels, and creams containing alcohol and soap have similar effects, but are not really quite as good as normal soap. Apart from the alcohol in soap, the antibacterial agents in these products don't affect the virus structure much at all. Consequently, many antibacterial products are basically just an expensive version of soap in terms of how they act on viruses. Soap is the best, but alcohol wipes are good when soap is not practical or handy, example, office receptions. But why exactly is soap so good? To explain that, I will take you through a bit of a journey through supramolecular chemistry, nanoscience, and virology. I try to explain this in generic terms as much as possible, which means leaving some specialist chemistry terms out. I point out that while I'm not an expert in supramolecular chemistry and the assembly of nanoparticles, I read that wrong. I point out that while I am an expert in supramolecular chemistry and the assembly of nanoparticles, I am not a virologist. The image with the first tweet is from an excellent post here which is dense with good virology info. I've always been fascinated by viruses as I see them as one of the most spectacular examples of how supramolecular chemistry and nanoscience can converge. Most viruses consist of three building blocks: RNA, proteins, and lipids. The RNA is the viral genetic material. It is very similar to DNA. The proteins have several roles, including breaking into the target cell, assist with virus replication, and basically to be a key building block, like a brick in a house, in the whole virus structure. The lipids then form a coat around the virus, both for protection and to assist with its spread and cellular invasion. The RNA, proteins, and lipids self-assemble to form the virus. Critically, there are no strong covalent bonds holding these units together. Instead, the viral self-assembly is based on weak, non-covalent interactions between the proteins, RNA, and lipids. Together, these act like a Velcro, so that it is very hard to break up the self-assembled viral particle. Still, we can do it, exampled with soap. Most viruses, including the coronavirus, are between 500 to 200 nanometers, so they are true nanoparticles. Nanoparticles have complex interactions with surfaces they are on. Same with viruses. Skin, steel, timber, fabric, paint, and porcelain are all very different surfaces. When a virus invades a cell, the RNA hijacks the cellular machinery like a computer virus and forces the cell to start to make a lot of fresh copies of its own RNA and the various proteins that make up the virus. These new RNA and protein molecules self-assemble with the lipids usually readily present in the cell to form new copies of the virus. That is, the virus does not photocopy itself, it makes copies of the building blocks which then self-assemble into new viruses. All those new viruses eventually overwhelm the cell and it dies/explodes, releasing viruses which then go on to infect more cells. In the lungs, some of these viruses end up in the airways and the mucous membranes surrounding these. When you cough, or especially when you sneeze, tiny droplets from the airways can fly up to 10 meters, that is 30 feet. The larger ones are thought to be main coronavirus carriers, and they can go at least 2 meters or 7 feet. Thus, cover your sneezes and coughs, people. These tiny droplets end up on surfaces and often dry out quickly. But the viruses are still active. What happens next is all about supramolecular chemistry and how self-assembled nanoparticles like the viruses interact with their environment. Now it's time to introduce a similarly powerful supramolecular chemistry concept that effectively says similar molecules appear to interact more strongly with each other than dissimilar ones. Wood, fabric, and not to mention skin interact fairly strongly with viruses. Contrast this with steel, porcelain, and at least some plastics, for example Teflon. The surface structure also matters. The flatter the surface, the less the virus will stick to the surface. Rougher surfaces can actually pull the virus apart. So why are surfaces different? The virus is held together by a combination of hydrogen bonds, like those in water, and what we call hydrophilic or fat-like interactions. The surface of fibers of wood, for instance, can form a lot of hydrogen bonds with the virus. In contrast, steel, porcelain, or Teflon do not form a lot of hydrogen bond with the virus, so the virus is not strongly bound to these surfaces. The virus is quite stable on these surfaces, whereas it doesn't stay active for long on, say, fabric or wood. For how long does this virus stay active? It depends. The SARS-CoV-2 coronavirus is thought to stay active on favorable surface for hours, possibly a day. Moisture dissolves, sunlight, UV, and heat, molecular motions, all make the virus less stable. The skin is an ideal surface for a virus. It's organic, and the proteins and fatty acids in the dead cells on the surface interact with the virus through both hydrogen bonds and the fat-like hydrophilic interactions. So when you touch, say, a steel surface with a virus particle on it, it will stick to your skin and hence get transferred onto your hands. But you're not yet infected. If you touch your face, though, the virus can get transferred from your hands and onto your face. Now the virus is dangerously close to the airways and mucus-type membranes in and around your mouth and eyes. So the virus can get in and voila, you're infected. That is, unless your immune system kills the virus. If the virus is on your hands, you can pass it on by shaking someone else's hands. Kisses, well, that's pretty obvious. It comes without saying that if someone sneezes right in your face, you're kind of stuffed. Part 2 about soap coming next. So, part 2, about soap, supramolecular chemistry, and viruses. So how often do you touch your face? Turns out most people touch their face once every 2 to 5 minutes. Yeah, so you're at high risk once the virus gets on your hands, unless you can wash the active virus off. So let's try washing it off with plain water. It might just work, but water only competes with the strong glue-like interactions between skin and virus via hydrogen bonds. The virus is quite sticky and may not budge. Water isn't enough. Soapy water is totally different. Soap contains fat-like substances known as amphiphilyls. I'm not sure on that one. Some structurally very similar with the lipids in the virus membrane. The soap molecules complete with the lipids in the virus membrane. The soap molecules also compete with a lot of other non-covalent bonds that help the proteins, RNA, and lipids stick together. The soap is effectively dissolving the glue that holds the virus together. Add to that all the water. The soap also outcompetes the interactions between the virus and the skin surface. Soon the viruses get detached and fall apart like a house of cards due to the combined action of soap and water. The virus is gone. The skin is quite rough and wrinkly, which is why you need to do a fair amount of rubbing and soaking to ensure the soap reaches every nook and nanny of the surface that could be hiding active viruses. Alcohol-based products, which pretty much includes all disinfectants and antibacterial products, contain a high percentage alcohol solution, typically 60 to 80% ethanol, sometimes with a bit of isopropanol as well as then some water and a bit of soap. Ethanol and other alcohols do not only readily form hydrogen bonds with the virus material, but as a solvent are more lipophilic than water. Hence, alcohol do also dissolve the lipid membrane and disrupt other supramolecular interactions with the virus. However, you need a fairly high concentration, maybe 60% of the alcohol, to get a rapid dissolution of the virus. Vodka or whiskey, usually 40% of ethanol, will not dissolve the virus as quickly. Overall, alcohol is not quite as good as soap at this task. Nearly all antibacterial products contain alcohol and soap and does help killing viruses, but some also include active bacterial killing agents like triclosan. Those, however, do basically nothing to the virus. To sum it up, viruses are almost like little grease nanoparticles. They can stay active for many hours on surfaces and then get picked up by touch. They then get on our face and infect us because most of us touch the face quite frequently. Water is not very effective alone in washing the virus off our hands. Alcohol-based products work better, but nothing beats soap. The virus detaches from the skin and falls apart very readily in soapy water. Here you have it. The supramolecular chemistry and nanoscience tell us that not only a lot about how the virus self-assembled into a functional active menace, but also how we can beat viruses with something as simple as soap. Thank you all. Thank you for reading my very first thread. Thank you for reading my first thread. Apologies for any mistakes in the above. I may have some virology details wrong here, as I am not a virologist like at McKay IM, whom I'm a big fan of, but I hope this inspires you not only to use soap, but to read up on chemistry. That was pretty cool. Go follow up Professor Pali Thordarson, or if that's how his name's pronounced. Well written and such. Anyway, I thought that was cool. Let me know what you think. Thanks for watching. Stay safe. Good luck, everyone.